Hello student, in this video I am going to prove this theorem that if a function is differentiable at a point A in its domain, then fx must be continuous at that point A. So before that, let me recall back the definition of a differentiable function at a point. A function is said to be differentiable at a point, say A, if limit h tends to 0, fa plus h minus f of a by h exists, or limit x tends to a, fx minus fa by x minus a exists. Number 2, a function fx is said to be continuous at x is equal to a if limit x tends to a, fx is equal to f of a, or limit h tends to 0, f of a plus h is equal to f of a. So using these two definitions, I need to show that the function which is differentiable at a point must be continuous at a point. So here, what is given in the statement? It's given that f of x is differentiable at a, which means that f of x limit h tends to 0, f of a plus h minus f of a by h exists. So let me name this as equation 1. And we know that the notation for this one is, we can denote or f prime of a exists. Since f prime of a is equal to limit h tend to 0, fa plus h minus f of a by h. Now, in order to show that fx is continuous, let us find out what is f of a plus h minus f of a. I need to show that limit of this one, h tend to 0, should be equal to 0. Now, f of a plus h minus f of a can be written as f of a plus h minus f of a whole thing divided by h into h. Multiply and divide by h. Then you see that if these two can be cancelled, then you get the original equation fa plus h minus f of a. Now, letting h tends to 0 on both sides, we have limit h tends to 0, f of a plus h minus f of a. This is equal to limit h tends to 0 on the left hand side, f of a plus h minus f of a by h into h. And this will implies that limit h tends to 0, f of a plus h minus f of a, this is equal to limit h tends to 0, f of a plus h minus f of a by h into limit h tends to 0, h. As we know that from the properties of limits of function, limit x tends to a, fx gx is same as limit x tends to a, fx into limit x tends to a, g of x. So by applying that property of limits of a function, then we can write this one as limit h tends to 0, fa plus h minus f of a by h into limit h tends to 0, h. Now, what is this one? The first limit exists since f is given to be differentiable at a point A, and it is denoted by f prime of A. So this will imply that limit h tends to 0, f of a plus h minus f of a, this is equal to f prime of a. Why this is possible? Because from the given statement, it's given that f is differentiable. So f prime of a will exist into, now what is limit h tend to 0, h. So since there is no, since the term in the denominator is 1, so we can straight away substitute the value of h by 0, so it will be into 0. So finally, what we have now, limit h tends to 0, f of a plus h minus f of a is equal to, this is 0, or limit h tends to 0, f of a plus h minus, since the second term is independent of h, so you can write it as limit h tend to 0, f of a is equal to 0. But limit h tend to 0, f of a will be f of a itself, because this function does not depend on h. So it implies that limit h tends to 0, f of a plus h, transfer this one to that side, then this will be equal to f of a. So by definition of a continuous function at a point a, this will imply that f of x is continuous at x is equal to a. So this shows that a function which is differentiable at a point will always be continuous at that point. However, the converse is not true. So let us give an example of this one. You can write here, however, the converse is not true. That is, a continuous function need not be differentiable. Let us take a particular example. Take fx is equal to the absolute value of x, or the modulus of x, where what is mod x by definition? This is equal to, it will be x if x is greater or equal to 0, and minus x if x is less than 0. It is defined as a piecewise function. It will be x if x is greater or equal to 0, and mod x will be minus x if x is less than 0. Now let us draw the graph of this one. As we all know that the graph of this function fx is equal to mod x is of this form. So now what we need to show is that at this point 0, that is, which is the origin, fx is not differentiable. That means we cannot draw a definite tangent or the definite slope at this point 0, 0, which is the origin. So let us show that by using the definition that the limit of the left hand derivative and the right hand derivative does not exist. This is the y-axis, this is the x-axis. Now here, what is f prime of 0? F prime of 0 is equal to limit x tends to 0, f of x minus f of 0 by x minus 0. By using the second definition of derivability of function at a point. So this is equal to what? It is limit x tends to 0, f of x. Now what is f of 0? F of 0, if you replace, excuse me, if you replace x by 0, then f of 0 will be 0 itself. So this one reduces to minus 0 by x, which is equal to limit x tends to 0, f of x by x. Now in this case, two cases arise. The first one is because fx is defined as mod x, where mod x is equal to x if x is greater or equal to 0, and minus x if x is less than 0. Then let us see what will be this one. Let us check whether the limit of this exists or not. This is equal to limit x tends to 0 mod x by x. Now, to show that this f prime of 0 does not exist, let us find out what is left hand derivative lf prime of 0. It is called limit x tends to 0 minus f of x minus f of 0 by x minus 0, which is called limit x tends to 0 minus. X tends to 0 minus means that in a number line, this is 0. That means x approaches 0 from the x approaches 0 from the left side of 0. So now it will be f of x by x will get here because f of 0 is 0. And this is called to limit x tends to 0 minus mod x by x. But now if x tends to 0 minus, that means x is negative. So in this case, what will be modulus of x? It has to be minus x by the definition that we have for the absolute value of x. See, if x is less than 0, then in that case, mod x has to be replaced by minus x. So since x approaches 0 from the left side means that x is negative. So this will be equal to, it is limit x tends to 0, limit x tends to 0 minus, it will be minus x by x. X can be cancelled, so this will be equal to minus 1. As minus 1 is a constant, so as x tends to 0 minus, it will remain as minus 1. And what about rf prime of 0, the right hand limit? It is limit x tends to 0 plus f of x minus f of 0 by x minus 0. Now x tends to 0 plus means that x approaches 0 from the right side of 0. That means x is positive. So this is equal to limit x tends to 0 plus f of x by x, because f of 0 is 0. And then what is modulus function? What is f of x? It is mod x. The limit x tends to 0 plus mod x by x. Now what is modulus of x? We define absolute value of x as x if x is greater or equal to 0. Since x approaches 0, in this case from the right side of 0, so it means that it is positive. So modulus of x has to be replaced by x only. So this is equal to limit x tends to 0 plus x by x. Now this can be cancelled. It gives you limit x tends to 0 plus 1, and this is equal to 1 because x tends to 0 plus of a constant number will be that constant number only. Now if I denote this as equation 2 and this one as equation 1, it will implies that LF prime of 0 from 1 and 2, this is not the same as RF prime of 0. Since the left hand derivative is not equal to the right hand derivative, therefore the limit of this one, f prime 0, that is the derivative of f prime of 0, this one does not exist. That means at the corner point or at this point here 0, we cannot have a definite slope or the definite tangent. So hope it is clear now with this example that the converse of the above theorem is not true. That is, every continuous function need not be differentiable.